Imagine a universe that is almost identical to our own. It has planets, stars, vast, swirling galaxies. Light zipping across the cosmos at incredible speed. All the fundamental building blocks of matter. Tiny particles that should, in theory, come together to form everything we see. But in this strange, parallel reality, there is a profound and unsettling difference. Nothing has any substance. Nothing has any mass. Every single particle, the smallest electron, the most complex atomic nucleus, would be a weightless phantom, condemned to travel at the speed of light. They could never slow down. They could never clump together. They could never form the intricate structures that make our existence possible. In such a universe, atoms would be an impossibility. Without mass, an electron could never be captured by a proton to form a simple hydrogen atom. The delicate dance between particles that governs chemistry and biology would simply not exist. No planets to stand on, no air to breathe, no stars to warm the cold emptiness of space. The rich tapestry of reality, from the chair you are sitting on to distant quasars billions of light years away, would dissolve into a fleeting soup of massless particles endlessly crisscrossing the void. This isn't just a strange thought experiment. For a long time, it was a deep and troubling puzzle at the heart of physics. Our best theories, for all their power and elegance, seem to predict exactly this massless reality. This discrepancy was one of the greatest mysteries of the 20th century. Our understanding of the fundamental forces of nature was incredibly successful. We had a beautiful mathematical framework that described how particles interacted, how light traveled, and how atoms held together. Yet this framework insisted elementary particles should have no intrinsic mass. This contradicted everything we observed. We knew particles had mass, we could measure it. An electron has a tiny but definite mass. A proton has a mass nearly 2,000 times greater. The universe is not a weightless phantom. So what was our theory missing? The problem was profound. It suggested a fundamental ingredient of reality had been overlooked. Something was giving the universe its substance. An invisible mechanism at the most basic level allowed particles to acquire mass, and thus allowed for the existence of everything. The quest to find this missing piece became one of the most ambitious scientific journeys ever undertaken. It required new ideas, new technologies on a scale never before seen, and the collective effort of thousands of minds over multiple generations. The story of this search is the story of how we discovered the true nature of reality itself. The mystery of mass haunted physicists for decades. The prevailing theory of particles and forces, known as the Standard Model, was a monumental achievement. It was like a map of the subatomic world, listing all the known particles and the rules for their interactions. It described the family of quarks. They build protons and neutrons. It described the leptons, like the familiar electron, and the force-carrying particles, the bosons. They act as messengers for electromagnetism. And the nuclear forces. The model was stunningly accurate in its predictions, tested and verified in countless experiments. It was, and still is, the most successful scientific theory ever created. But it had a gaping hole, a ghost in the machine. The mathematics at the core of the Standard Model was built on a powerful idea: symmetry. In physics, symmetry is a profound concept that dictates the laws of nature. It suggests that the underlying rules of the universe should be elegant and consistent. However, the elegant symmetry of the Standard Model demanded that all fundamental particles be massless. To give them mass, you had to break that symmetry. But doing so in a clumsy way would shatter the entire theory, rendering all its successful predictions meaningless. It was a paradox. To explain the universe we see, we had to find a way to break the symmetry without destroying the beautiful mathematical structure that relied on it. This is where a bold and radical idea emerged in the 1960s. A handful of theoretical physicists, working independently, proposed a solution. What if the universe wasn't empty? What if, permeating all of space and time, there was an invisible universal energy field? This field would be everywhere, like a cosmic molasses filling the void. It wouldn't be one of the known forces, but something entirely new. Most particles would travel through this field without interacting with it at all, just as light travels through a pane of glass. But other particles would interact with it, dragging against it as they moved. This interaction, this drag, is what we perceive as mass. The idea was revolutionary. Mass wasn't an intrinsic property of a particle. It was a consequence of its relationship with this invisible field. A particle with a large mass was simply one that interacted strongly with the field, like trying to wade through deep water. A particle with a small mass was one that interacted weakly, like skipping across the surface. And a massless particle, like the photon of light, didn't interact with it at all, allowing it to travel unimpeded at the ultimate cosmic speed limit. This invisible energy field was given a name: the Higgs field. It was the ghost in the machine, the missing component that could solve the mystery of mass. The concept of the Higgs field was a brilliant theoretical leap. It solved the mass problem while preserving the elegant symmetries of the standard model. It was a beautiful idea, a perfect suspect for the crime of giving the universe its substance. But in science, ideas are not enough. You need evidence. You need proof. And this is where the detective story truly began. If this invisible field really existed, there had to be a way to detect it. The theorists predicted that, if you could excite it with enough energy, the field would produce its own particle, a ripple in the field itself. This particle was the smoking gun. It was named the Higgs Boson. Finding this particle would be the ultimate confirmation. It would turn a clever mathematical trick into physical reality. But the prediction came with a daunting challenge. The theory couldn't tell us the exact mass, only that it would likely be very heavy. In particle physics, heavy means enormous energy to create. You couldn't just find a Higgs lying around. You had to forge it in a crucible of unimaginable power. You would need to smash other particles together at nearly the speed of light, and hope that, in the fleeting fireball, a Higgs might flicker into existence for a fraction of a second. This set the stage for a monumental hunt, spanning half a century, a journey that pushed the boundaries of technology and human ingenuity. It required the largest and most complex machine ever built, the Large Hadron Collider at CERN. This colossal 27-kilometer ring, buried deep beneath the French-Swiss border, was designed to create the conditions to find the Higgs. It was a gamble on a scale never seen before, costing billions and requiring thousands of scientists from over 100 countries. All of this effort focused on finding one elusive particle. Our journey will follow the clues of this epic scientific mystery. We will start by exploring the map of the subatomic world, the standard model, and the beautiful symmetries that puzzled physicists. Then we will delve into the Higgs field and the symmetry-breaking mechanism that gives reality its weight. Finally, we will join the hunt, witness the race to build the LHC, and the nail-biting search through mountains of data. It is a story of curiosity, persistence, and a single idea that rewrote our understanding of the cosmos. The birth of this revolutionary idea was not the work of a single mind, but a remarkable case of parallel thinking. In the summer of 1964, a flurry of scientific papers was published that, taken together, laid the entire theoretical groundwork for the Higgs mechanism. The story begins with a paper by two Belgian physicists, Robert Brute and François Englert. They were the first to publish, showing in detail how a universal field could spontaneously break a symmetry and give mass to force-carrying particles. Just a few weeks later, a Scottish physicist working in Edinburgh named Peter Higgs wrote a short paper outlining a similar mechanism. However, when he submitted it to a physics journal, it was rejected. The referees felt it was an interesting mathematical idea, but had no obvious connection to the physical world. Spurred on by this rejection, Higgs revised his paper. He added a crucial new paragraph at the end, in which he explicitly pointed out that his theory predicted the existence of a new, massive particle, the ripple in the field. This revised paper was accepted and published. As the search began to ramp up, it acquired a new, more controversial nickname. In 1993, Leon Lederman published a popular science book about the search for the Higgs. He wanted to call it the goddamn particle to express the frustration physicists felt. His publisher thought the title was too provocative. They shortened it, and the book was published under the title, The God Particle. The name stuck. Most physicists dislike it. It implies a religious or divine connection that has nothing to do with the science. The Higgs boson is not divine. It is a natural physical phenomenon, a part of the universe we can study and understand through the laws of physics. In a metaphorical sense, the Higgs field played a godlike role in the story of creation. It bestowed the property of mass upon some, while leaving others massless. Without the Higgs mechanism, there would be no atoms, no planets, no stars, and no people. So while physicists might cringe at the name, the God particle does capture something of the profound, almost mythical importance of the Higgs boson. The theory was beautiful, the stakes were high, the particle had a catchy nickname. But one enormous problem remained. No one knew exactly where to look. The theory of the Higgs mechanism could not predict the mass of the Higgs boson itself. It was like being told to find a needle in a haystack without knowing whether the needle was as small as a pin or as large as a pitchfork. Creating a Higgs is an act of incredible violence and rarity. In the tiny fireball, the energy can momentarily create new, heavy particles that don't normally exist. But very, very rarely, less than 1 in a billion collisions, the conditions might produce a fleeting Higgs. The Higgs is incredibly unstable. It would decay into other, more common particles almost instantly. You could never see the Higgs directly. Instead, you sift through the collision debris, searching for a very specific combination of decay products, a signature of the parent particle. Previous generations of particle accelerators had searched for the Higgs at lower energies and had come up empty-handed. By the 1990s, it became clear that if the Higgs boson existed, finding it would require a machine more powerful than anything ever conceived. This led to the conception of the Large Hadron Collider, or LHC, at CERN. The plan was to build a 27-kilometer-long circular tunnel and line it with thousands of the world's most powerful superconducting magnets. Building the LHC was one of the greatest international scientific collaborations in history, involving over 10,000 scientists from more than 100 countries. This is colder than the empty space between the stars, making the inside of the LHC one of the coldest places in the entire universe. The LHC was, in essence, a time machine designed to briefly wind the clock back 13.8 billion years. It was a modern-day cathedral of science, a monument to human curiosity built not to worship a god, but to question the very fabric of reality itself. Inside the vast, circular tunnel of the LHC, two beams of protons are accelerated in opposite directions. Each bunch contains about 100 billion protons. They race around the 27-kilometer ring over 11,000 times every second. It's like firing two needles from 10 kilometers apart and having them meet halfway. Most simply, fly past each other. When bunches cross, they create a storm of collisions, up to 40 million times every single second inside the detectors. Each collision annihilates the protons in a tiny fireball of pure energy. That energy crystallizes into a spray of new particles. Physicists hope it will, very rarely, produce a Higgs boson. To capture this information, physicists built gargantuan detectors, essentially giant, three-dimensional digital cameras. The sheer volume of data produced by these detectors is mind-boggling, about 1 petabyte of data every second. It is simply impossible to store and analyze this much information. An ultra-fast, multi-level trigger system acts as a filter. Of the 40 million collisions per second, the trigger system selects only the most promising 1,000 events. This mountain of data is distributed around the world using a sophisticated network called the Worldwide LHC Computing Grid. It allows thousands of physicists, wherever they are in the world, to access the data and contribute to the collective search. The search was not conducted by a single experiment, but by two large independent teams, ATLAS and CMS. They were deliberately designed and built using different technological solutions and engineering philosophies. If one experiment saw a hint of a new particle, but it was just a glitch, the other experiment would not see it. But if two completely different experiments saw the exact same signal at the exact same mass, it would provide powerful, independent confirmation that the signal was real. Alongside the two giants, ATLAS and CMS, two smaller, more specialized experiments also operate at the LHC, ALICE, and LHCb. Together, these four experiments ensured that every aspect of the LHC's high-energy collisions was scrutinized in detail. After years of construction, the Large Hadron Collider finally began its high-energy physics program in late 2009. By 2011, whispers and rumors began to circulate within the physics community. Both the ATLAS and CMS teams were starting to see something, a small but persistent excess of events in the same narrow mass region, around 125 giga-electron volts. It was a tantalizing hint, but it was far from a discovery. It could be a random fluctuation. The standard for a discovery in particle physics is extremely high, 5 sigma, less than a 1 in 3.5 million chance that the observed excess is just a random fluke. In late 2011, the hints were only at the 2 or 3 sigma level. It was exciting, but it wasn't proof. Throughout the first half of 2012, the LHC ran flawlessly, delivering a new torrent of data. As spring turned to summer, the statistical significance of the small excess began to grow. The bump around 125 GeV became more pronounced. They decided to present their findings at a special seminar at CERN on July 4, 2012. Peter Higgs, Francois Englert were invited to attend in person. On the day of the announcement, the CERN auditorium was packed. When the final plots were shown, both experiments had independently reached 5 sigma. The auditorium erupted in applause. The bump in the graph was the ripple in reality, the signature of the Higgs boson. After a 50-year search, the missing cornerstone of the Standard Model had been found. Peter Higgs was seen wiping a tear from his eye. The detective story that had spanned generations had finally reached its stunning conclusion. The ghost in the machine was a ghost no more. The discovery of the Higgs boson was far more than just adding another particle to the subatomic zoo. It was the placement of the final, crucial cornerstone of the Standard Model. By confirming the existence of the Higgs field, the discovery validated the theory of spontaneous symmetry breaking. Mass, we now understand, is not an intrinsic property of particles. It is an environmental one, gifted by the Higgs field. With the Higgs in place, the Standard Model is now a complete theory of the everyday world. It is the most successful scientific theory ever devised by humankind. However, a complete picture is not necessarily the final picture. The completion of the Standard Model also defines its limits. We now have a near-perfect map of the 5% of the universe that is ordinary matter. About 27% of the universe is dark matter. About 68% of the cosmos is dark energy. We simply do not know. Then there are other deep questions. Why are the masses of the fundamental particles so wildly different? These unanswered questions tell us that the Standard Model, for all its glory, is not the final theory. The Higgs boson itself might be a window to this new physics. By studying its properties, we might find tiny deviations, providing the first clues to what lies beyond. The discovery of the Higgs boson was the triumphant scaling of a mighty peak, but from its summit, we can now see a whole new range of even taller mountains on the horizon. The journey is far from over. The greatest detective story continues, and the universe is still full of mysteries, waiting for the next generation of explorers to come and solve them.